So question 1 is asking us to find the volume of the solid below the surface. Z equals natural log of x is located in the first octant and bounded by x equals 4, y equals 0, and y equals the natural log of x minus 2. All right, so we can get a look using GeoGebra at z equals the natural log of x. I can delete that. Z equals ln of x. As you know, I don't love the plane. I prefer the grid. Everybody's different though. All right, so this is what I look like. I just do a quick look. So we have some, it's clearly natural logarithmic in nature, but it's got elements of a plane. So basically like a plane that's been bent to follow a profile of a natural log. Right, so that's kind of cool. All right, so it's bounded by x equals 4, y equals 0, and y equals the natural log of x minus 2 in the xy plane. So let's actually just do a quick sketch of that. All right, x equals 4, vertical line. I'll just kind of pop it right over here. Y equals 0, horizontal line, the x-axis. And then when it comes to the natural log of x minus 2, we can do a quick sketch if we want. We can plot it if we want a little bit more accuracy. But basically, I mean, you know what a natural log looks like. You just need your vertical asymptote, which is at 2, and your x-intercept, which is going to be at 3. But you just probably so 1. Oh, let me just scale it a little bit better. So vertical asymptote, x-intercept. So it's going to look something like this. But you could also, like I said, put it in Desmos. Too many y's. Y equals ln, just type in the ln this time, of x minus dos. And you get that equation, or that graph, I should say. All right, so it's in the first octant, so it's going to correspond with the first quadrant, or correspond to the first quadrant in the xy plane, right, as the base region. So a little bit of smidge here. That's what we're focusing on. All right, so we would need to restrict our domain for x and y based off of that information. All right, in terms of just a comparison between the surface and the bounded region, I'm not seeing anything that looks circular here, so I'm not thinking cylindrical or spherical coordinates. Now, you could also consider something like a change of coordinates within the xy plane, by a transformation. But I'm seeing a region that's adjacent to the x-axis, so I think we're going to be okay in that regard also. All right, so double integral. We're looking at z equals the natural log of x. Now it's just a question of how we want to bound it. Do we want to bound it with respect to x first and then y, or vice versa? So we have an equation that's defined as y equals the natural log of x minus 2, so in the form of y equals. So if we just kind of bring it in on that bounded region, we'd be looking at y values that are spanning from the x-axis to the curve itself. All right, so now we would just have to limit that to only the interval between, this would be 3 and this would be 4. So going the other way, and so we'd be in good shape. So I think that's pretty easy in terms of bounding conceptually. Now, carrying it out through the integration process might be a little bit of a different story, but we'll see. All right, so y equals the natural log of x minus 2. And then x equals 0, I'm sorry, not 0, 3 to 4. All right, so we did the y first, and then we did the x. All right, now as far as the y's are concerned, integrating with respect to y, I should say, I think that's probably okay to leave it as is. I mean, it's definitely okay, because when you integrate an x function with respect to y, we're just slapping a y on it. So this is y ln of x over the interval of 0 to the natural log of x minus 2. Pop in a 0, you're going to get a 0, so I'm not worried about the lower bound. So we're looking at ln of x minus 2 times ln of just a plain old x. That's integrated over the interval of 3 to 4 with respect to x. Now, if I had to do that by hand, okay, it might be a little bit of a ride, but we don't, because I can just pop this right on in. All right, so miscellaneous, going from 3 to 4, natural log x minus 2, close it up, throw a multiplication symbol in there if you want, but I'm just going to write ln of x, close it up, and a nice dx off at the end, and we're looking at approximately 0.499. Let's see, any rounding instructions? No, so let's just go 0.499. Leave it like that. And you know, if it ends up being the case where you have to round it, you know, maybe go 0.5, or you know, just follow the instructions. You know, the second part, it really isn't something you would see on a test. This is just to make sure that you're aware that, you know, even though this is a fill in the blank, just calling for an answer on the practice test, on the real test, it could be a case where you have to submit your supporting work. All right, so just be mindful of that and you'll be okay. So we have an incomplete iterated integral. We need to find the volume that lies under the plane 2y plus 2z equals 8, and above the disk x squared plus y squared equals 1. All right, so we're looking at something that is circular in nature. We have an elliptical intersection here. We have a circular base region. So if I want to find the volume, I'd be looking at a double integral in cylindrical coordinates. All right, so the z equation, well, I can modify that in a sec, but if I'm doing it in cylindrical, it would be z r dr d theta. All right, so now my bounds would be important, obviously. For the base region, I'm looking at something, like I said, circular. It does appear to be the entire circular region. So the radius of which x squared plus y squared equals 1. Oops. Do that. Do the whole thing. X squared plus y squared equals 1, radius of 1. Ooh, that's strange. And it does appear to go from 0 to 2 pi all the way around. All right, I put it into GeoGebra real quick so we can just verify that. And it does seem to go all the way around, and it does seem to have, if I can get a top-down view that looks reasonable, it does seem at first glance to have a radius of 1. All right, or second and like 10th glance. All right, so we're good there. So I would be saying 0 to 1 and 0 to 2 pi, but we do want to bear in mind that the integral that they gave us has an upper bound of pi, so we'll cross that bridge in a minute. Well, let's take a look at z. Z would be equal to, well, originally it was 2y plus 2z is equal to 8. So z would be, you're going to subtract the 2y, so 8 minus 2y, and then we're going to divide by the 2. So z is really the same as saying 4 minus y. Now, if I want it in cylindrical coordinates, I would replace the y with a r sine of theta. And r sine of theta. So, my double integral, let me just do a quick reproduction, is going to have, instead of the z, it's going to have the 4 minus r sine of theta multiplied by the r that's already there, would give us the integrand that they told us in the problem. So that's good news. We're on the right path here, at least. All right, so that's all of this. If I distribute, that'll be equivalent, which means that C must be dr d theta. So in Blackboard, we would just have to write out theta, which is fine. It's a little aggravating, but it's doable easily. The B value is a 1. That's also pretty easy. The A value, well, if they made this upper bound into a pi, what they're saying is that they split the region in half. So they're going only across the northern hemisphere, to use that term loosely. They're disregarding the bottom half. Now that would only work if there was symmetry about the y-axis in our graph, I'm sorry, about the x-axis. And if I just stop the diagram here, or the rotation here, you could see that there is symmetry. So we have equal parts to the left and to the right of the x-axis. So we're in good shape here to just simply take that 2 and make it a coefficient. All right, so 2 multiplied by the integral over the interval of 0 to 1, then 0 to pi, would get the job done. All right, so that would be a 2. All right. So number 3 is saying the volume inside the, or the volume of the solid inside the sphere of x squared plus y squared plus z squared is equal to 16. And outside the cylinder, x squared plus y squared is equal to 4, that is located in the first octant, represented as a triple integral in spherical coordinates, would be which of the following. All right, so triple integral, it's outside of the cylinder, x squared plus y squared equals 4, so let me delete. Inside the sphere, all right, so what we're looking for is a portion of the sphere related to the region that's bounded out, or the portion of the volume of the sphere, I should say, that's outside of the cylinder. All right, so but only in the first octant. Right, so to make this as complicated as possible, what I'll do though is I'll just do a quick snip and bring it in so I can mark it up. So we only care about the XY, I'm sorry, the first octant, so between the positive x-axis and the positive y-axis. if I can make that look halfway decent. Not really. Sort of. There, last attempt. Alright, that's alright. And then I'll get my z-axis in there. Alright, so we have that little cutoff here. That's only going to be really just kind of a little portion of the graph of that cylinder. Alright, so, you know, just kind of pretend this doesn't look terrible as you kind of had to make the adjustment throughout the course of the semester. So that's just getting worse and worse. Anyway, so again, outside the cylinder, but inside the sphere. So it would make sense for us to figure out the intersection between the two, all right, where one ends and the other begins. So we have x squared plus y squared plus z squared is equal to 16. And we know x squared plus y squared is equal to 4. So that would be the same as saying, by direct substitution, 4 plus z squared is equal to 16, which means z squared is equal to 12, which means z is equal to plus or minus the square root of 12. All right, so we can hold that piece of information. All right. Now, in terms of a rho value, we're looking for the distance outward. We can work off of the definition of z, or the equality for z in spherical coordinates would be rho cosine of phi is equal to, we can clean this up, plus or minus 2 radical 3, in which case we'd be looking at rho is equal to plus or minus 2 radical 3 times, or well, really divided by cosine, which would become secant. Right, so plus or minus 2 radical 3 secant of phi. All right, so we could define, and you could see based off of the bounds that were given, a fair few of them have 2 radical 3 secant of phi in them. All right, since we're only looking at the first octant, I'm not concerned with any negative rho values, but also I wouldn't be concerned with them anyway, because that just implies direction, which would be picked up, direction from the origin, which would be picked up by any angle, theta or phi that we incorporate. So rho would be equal to 2 radical 3 secant of phi. All right. So it is dependent on what the phi value is, but once we have that, then we're in pretty good shape. All right. So then, let's say, for example, let me get a different color here. We're going with blue. Let's say, for example, I'm living with, let's say, this point right here. All right. That point is going to have some corresponding movement in the xy plane of theta. It's going to have some sort of angular movement in space from the z-axis that we call phi. Right? We want to be thinking about what the most either of those values can be. And also we want to be thinking about the most that we can have in terms of a rho value. Well, the most that we could have is the extent of the sphere, which has a radius of 4. All right? Because it's a sphere with radius of 4. So if I had a point that, let's say, for example, was here, that would be on the innermost edge of what would be allowable in terms of the bounded volume that we're interested in. All right, anything out here is okay. We're not worried about this. But anything inside in this region here is going to be a problem. All right, so I would want to figure out the lowest extent of allowable values of phi in order to properly come up with my triple integral. All right, so fortunately I have handy dandy right triangle trig to work with. So if we look at this quickly but carefully, we know that the hypotenuse ought to be 4. Now, the cylinder is defined as x squared plus y squared equals 4, which means that it has a radius of 2. All right, so just using ordinary SOHCAHTOA, we have opposite over hypotenuse. The sine of phi is equal to 2 over 4. Sine of phi is equal to a half. In the first quadrant, that occurs when the angle is equal to pi over 6 or 30 degrees. So that tells me, you know, with our ordinary bounds, I keep saying that, variables of integration, order of integration of rho squared sine phi d rho d phi d theta, that the rho values would go from 0, would go from 2 radical 3 times the secant of phi on up to 4. But my phi values, if we're going to think about how, you know, like how far out that this could go, we know that the minimum it could be is pi over 6, but if it were to extend downward following the circumference of the sphere and land in the first octant, you know, XY plane first octant, the most it could ever go would be pi over 2. All right, so you start kind of narrowing down the choices here. And you can see here that we're down, well, these are gone now. So it's going to be one of these two. So it's just a question of how far are we going to go in terms of theta. Well, again, first octant, so I only want to go a quarter of a turn, so 0 to pi over 2. So that's going to be this one. So for this question, number 4, we're looking to find the surface area. It's really part of a plane that's bounded by the intersection of that plane and the cylinder, which is going to be in the form of an ellipse. All right, so if we could figure out the equation of that ellipse, then we'll be in good shape. All right, so we're looking for the part of the xy plane corresponding with that. All right, so those would be our restrictions. So we have our z equation. I'll write it as f of x comma y is equal to 1 plus x. F sub x is equal to 1. F sub y would be equal to 0. So when I set up my double integral, square root of 1 squared plus 0 squared plus 1 squared dA, right? Because we haven't decided what coordinate system we're going to use, over some region R, right? So then it's just a matter of saying, okay, well, what is the most appropriate region to use? So first we'll clean this up. This is radical 2. We got my dA and the R. Now that's a cylinder. So how do we define that cylinder? Well, the issue that we're going to run into here is that it's not bounded, bounded, overused term. It's not symmetric about the z-axis. right? So defining it as just a simple r equals is going to be a tall order, right? We could do it in rectangular coordinates, and that's going to have its own challenges, but technology-wise, it's going to be something that can be handled. It just might involve a little bit of typing. All right, so if I want to come up with that equation, again, we're looking at something that's not centered around the origin. In 3 dimensions, that would be the z-axis. We have 1, 2, 3, 1, 2, 3, 4 as our center, with a radius of 2. We're looking at this, more or less. If I'm bounding this in terms of y, I'm going to need the 2 halves of this circle, the bottom half, the top half. So I could look at it as, we have x minus 3 squared plus y minus 4 squared is equal to 4. Bring over the x minus 3 squared, so y minus 4 squared is equal to 4 minus x minus 3 squared. Root both sides. I won't skip the step. Four minus x minus 3 squared under the radical, add a 4. So that would be our restriction, going from 4 minus that whole radical to 4 plus that whole radical. All right, now in terms of the x would be on the interval, I mean, you just look at the picture, the center's at 3, 4, reduce the x value by 2 and increase it by 2, we're going from 1 to 5. It's a little off with the scale, but you get the idea. All right, so 1, 5. All right, so x is over the interval of 1 to 5. All right, so if you don't mind doing some typing, then you can pop this right in and come up with the double integral over the interval of 1 to 5, then 4 minus 4 plus, then we have a radical 2 dy dx. So then we would just crunch it. The alternative to that would be to kick it over into cylindrical coordinates. So integrating with respect to y is not going to be difficult. So radical 2y over the intervals given. Or stated, I should say. So radical 2 times the upper minus radical 2 times the lower integrated over the interval of 1 to 5 dx. So that's going to go into Desmos. So function miscellaneous 1 to 5. I could factor out a radical 2 from the whole thing if I want. I'm just going to leave it in. 'Cause I'm probably, knowing my strengths and weaknesses, it's the kind of thing I like to screw up. Alright, so. Alright, so I got that, the radical 2 times the upper bound. Now I need the radical 2, so minus radical 2 times the lower bound. So 4 minus the square root of 4 minus x minus 3, close it up, square it. And then close it up for the integrand, and dx. And we're looking at about 17.8. And the direction set to round to the nearest tenth, so that's where we're at. 17.8 square units. Alright. So for number 5, find the Jacobian determinant, or just the Jacobian of the function with the given components. Alright, so a multiple choice question, but it might not be a multiple choice question on the test. Alright, so I have 3 equations, 3 variables, so I'd be looking for y1 partial with respect to x1, x2, and x3. And then the same thing for y2 and y3. So I just need to erase and rewrite. Alright, so that's what we're ultimately looking for. So Jacobian determinant, not just a Jacobian matrix. Alright, so with respect to x1, that makes only this part relevant. Alright, so that's going to give me a sine x sub 2. With respect to x sub 2, again, same piece is relevant. Derivative of sine is cosine, so we're going to have x sub 1 cosine x sub 2. Then with respect to x sub 3, it's just the last term that's relevant, so 1 over x sub 3. Alright. Now for the second equation, with respect to x sub 1, goes to 0 because there is no x sub 1. With respect to x sub 2, we hang on to the x sub 3, e to the x sub 2, times the derivative of x sub 2 with respect to x sub 2 is going to be 1, so no need to multiply there. And then with respect to x sub 3 is just going to be e to the x sub 2. And then the last one, the easy one, with respect to x sub 1 is 1, and with respect to the other variables, would be zeros. All right, and that's probably the best we could hope for. Because it allows us to find the determinant across the third row using the cofactor technique. Or it looks like, since we're dealing with something that is very close to a triangular matrix, if you wanted to try to modify using some, if you know your elementary row operations, you can try to clean it up so that it is triangular, and you can go from there. But this one isn't really that bad because it's really just going to end up being the determinant of these entries. All right, so that's going to be nice. All right, so, all right, I mean, as nice as it can be. So we're looking at -1 to the 3 plus 1 power multiplied by the entry of 1 multiplied by the determinant of this 2 by 2 square matrix. Alright, so these are irrelevant. They both go to 1. So diagonal down, e to the x squared x sub 1 cosine x sub 2 minus diagonal up. So x sub 3 e to the x sub 2 times 1 over x sub 3. Alright, so cancel here, cancel there, cancel here and there and everywhere. So this is what will remain, just without this guy here. We have a common e to the x squared, x sub 2, I should say. I should take a look at what the choices are, and keep an eye on that. So it looks like, yeah, if we factor out the e to the x sub 2 as a GCF, then we'll have something that looks exactly like one of the choices. And isn't that what the point is of this whole thing? So it looks like it's this one.